Hello, and welcome. I'm so glad you found your way here tonight, to this quiet moment we can share together. Perhaps you've had a long day, or perhaps your mind has been busy with thoughts that won't quite settle. Either way, you're welcome to rest now, to let your shoulders drop, to breathe a little deeper. You don't need to do anything at all except listen, if you'd like, or simply let these words become a soft background hum as you drift towards sleep. Tonight, we're going to travel together to a place that exists in near total darkness, in coolness, in silence, so profound it feels like the very definition of peace. We're going beneath the surface of the ocean, down past the waves and the light, to explore the ancient, patient geological formations that rest on the seafloor. These are structures built over millions of years, shaped by forces so gradual and gentle that they unfold in a timescale beyond our hurried human lives. There's something deeply calming about that, don't you think? The idea that while we rush through our days, far below the surface, stone is slowly becoming, mountains are quietly rising, and the earth is breathing in rhythms we can barely imagine. If you enjoy this kind of gentle journey into science, you're welcome to follow along for more. But there's no pressure, no urgency. Right now, just be here. Let's begin. The ocean floor is not flat. If you could somehow drain all the water away and stand at the edge of a continent, looking out, you would see one of the most dramatic landscapes on Earth. The seafloor descends in great terraces and slopes. It rises into mountain ranges taller than the Himalayas, and it splits open in valleys so deep they could swallow whole cities without a trace. But because all of this lies beneath miles of water, hidden from our everyday view, it exists in a kind of serene obscurity, unbothered by weather, untouched by wind. The water above acts as a blanket, muffling everything, softening everything, holding it all in a timeless, gentle suspension. Let's start with the continental shelf, that broad, shallow ledge that surrounds most of the world's land masses. This is where the ocean is still relatively shallow, often just a few hundred feet deep, and the seafloor slopes away from the coast, so gradually you might not even notice if you were walking along it. The continental shelf is made of the same kind of rock as the continents themselves, ancient granite and sedimentary layers that have been there for hundreds of millions of years. It's a place of transition, where the land meets the sea in the gentlest possible way. Rivers carry sediment down from the mountains and deposit it here, layer upon layer, year after year, building up a soft blanket of mud and sand that covers the harder rock beneath. It's quiet work, this accumulation. Grain by grain, the earth remakes itself. Beyond the shelf, the seafloor begins to drop more steeply. This is the continental slope, a long, descending ramp that leads down into the true deep ocean. The slope is not a cliff, not a sudden plunge, but a gradual tilting, a slow goodbye to the sunlight. As you descend, the water grows colder, the pressure increases, and the light fades from blue to twilight to black. The continental slope is often carved with deep channels, like riverbeds, where underwater avalanches of sediment have tumbled down over thousands of years. These are called submarine canyons, and some of them rival the Grand Canyon in scale. But unlike their terrestrial cousins, these canyons are filled with cold, still water, and they rest in perpetual darkness. There is something profoundly restful about imagining such a place. Vast, silent, untouched by the sun, a landscape that has known only the slow passage of time. At the base of the continental slope lies the continental rise, a gentler incline where sediment has piled up in enormous fans, spreading out across the deep ocean floor like a soft apron. This is where the debris from the continents finally comes to rest, settling into layers that will, over millions of years, compress into solid rock. The rise is a place of accumulation and patience, where the earth takes its time, where nothing is rushed. If you could sit on the seafloor here, You would feel the weight of the water above you, but also a strange kind of comfort in the stillness, in a knowledge that you are resting on layers of history, on the compressed memory of ancient rivers and mountains long since worn away. And then, beyond the rise, stretches the abyssal plain. This is the true floor of the ocean, the vast, flat expanse that covers more than half of the Earth's surface. The abyssal plain is one of the flattest places on the planet, a nearly level surface that extends for thousands of miles in every direction. It lies at depths of 10,000 to 20,000 feet, far beyond the reach of sunlight, far beyond the influence of storms. The water here is just a few degrees above freezing, and the pressure is immense, hundreds of times greater than at the surface. Yet life exists here, and the seafloor is not barren. It is covered with a fine, soft sediment called ooze, made from the remains of tiny organisms that have drifted down from the sunlit waters above. This ooze accumulates at a rate of about 1 centimeter every 1,000 years. Think about that for a moment. 1 centimeter, 1,000 years. It's a pace so slow it redefines the very idea of change. And there's something deeply soothing about that kind of timescale, a reminder that not everything needs to happen quickly. The abyssal plains are interrupted, here and there, by seamounts. These are underwater mountains, volcanoes that rose from the seafloor millions of years ago and then fell silent. Some seamounts reach to within a few hundred feet of the surface, while others remain deep beneath the waves, their peaks lost in the darkness. Seamounts are often isolated, solitary features rising from the flat plain, and they create their own small ecosystems, their slopes providing a foothold for corals and sponges, their presence altering the flow of deep ocean currents. But even in their grandeur, seamounts are quiet. They do not erupt. They do not tremble. They simply stand, patient and still, monuments to forces that have long since faded. Some seamounts are flat-topped, and these are called guyots. They were once volcanic islands that rose above the surface of the ocean, but over millions of years, waves eroded their peaks, grinding them down to flat platforms. Then, as the seafloor slowly subsided, or as the ocean level rose, these flat-topped mountains sank beneath the waves, becoming submerged pedestals in the deep. Guyots are evidence of deep time, of the way the Earth's surface is always moving, always changing, but so slowly that we can only see the results, never the process itself. They remind us that even mountains are temporary, that even stone yields to time, and that everything, eventually, returns to stillness. In the middle of the ocean, far from any continent, there is a feature that runs like a seam through the Earth's crust. This is the mid-ocean ridge, the longest mountain range on the planet, stretching for more than 40,000 miles through the Atlantic, Pacific, Indian, and Arctic oceans. The mid-ocean ridge is not a single, continuous mountain, but a vast, branching system of underwater peaks and valleys, all connected, all part of the same immense geological process. The ridge marks the place where two of the Earth's tectonic plates are slowly pulling apart, and as they separate, molten rock from deep within the Earth rises up to fill the gap. This molten rock cools and solidifies, becoming new seafloor. And in this way, the ocean basins are constantly being renewed, constantly being born. The process is called seafloor spreading, and it happens at a pace of just a few centimeters per year, about as fast as your fingernails grow. That's all, a few centimeters. But over millions of years, those centimeters add up, and entire ocean basins open, continents drift apart, and the map of the world is redrawn. The mid-ocean ridge is the engine of this process, the place where the Earth creates itself, and yet it does so in near total silence, in darkness, in a slow, steady rhythm that has continued for hundreds of millions of years. There is something profoundly calming about this, the idea that the Earth is always making itself new, always healing, always growing, but never in a hurry. At the center of the mid-ocean ridge is a rift valley, a deep, narrow trench where the two tectonic plates are pulling apart. The Rift Valley is the newest part of the seafloor, the place where molten rock is just now cooling into solid stone. The valley floor is often rough and broken, covered with fresh lava flows that have solidified into twisted, ropey shapes called pillow lava. Pillow lava forms when molten rock erupts underwater and cools so quickly that it forms rounded, bulbous shapes like a pile of cushions. These pillows are a sign of creation, of the Earth's inner heat meeting the cold ocean, and they rest there on the Rift Valley floor, undisturbed, slowly being buried by sediment as the seafloor spreads away from the ridge. Along the mid-ocean ridge, there are places where the Earth's heat breaks through in dramatic fashion. These are hydrothermal vents, underwater hot springs where superheated water, rich in minerals, erupts from cracks in the seafloor. The water can reach temperatures of 700 degrees Fahrenheit, hot enough to melt lead, but it doesn't boil because of the immense pressure at these depths. Instead, it rises in shimmering plumes, carrying with it dissolved minerals from deep within the Earth. When this hot water meets the cold ocean, the minerals precipitate out, forming towering chimneys of rock that can grow several stories tall. These chimneys are called black smokers or white smokers, depending on the color of the minerals they emit, and they're some of the most otherworldly structures on the planet. But despite their dramatic appearance, hydrothermal vents are also places of life and strange tranquility. The minerals in the vent water provide energy for bacteria, which form the base of a unique ecosystem that exists without sunlight, without photosynthesis, relying entirely on the Earth's internal heat. Tube worms, clams, shrimp, and crabs cluster around the vents, living in the warm water, thriving in conditions that would be lethal to most surface-dwelling creatures. It's a reminder that life is adaptable, that it finds a way even in the deepest, darkest, most unlikely places, and that the Earth provides quietly and steadily for those who can learn to live with its rhythms. Hydrothermal vents don't last forever. The seafloor is always spreading, always moving, and as the rock around a vent is carried away from the ridge, the vent eventually goes cold and dies. The chimney remains, a fossil of a once active system, slowly being buried by sediment or toppled by currents. But new vents are always forming at the ridge, and the cycle continues, a slow dance of creation and decay that has been going on for as long as the oceans have existed. There's a kind of peace in that continuity, in knowing that the Earth is always renewing itself, always finding new ways to express its inner warmth. Away from the mid-ocean ridges, on the far side of the ocean basins, the seafloor begins to descend once more. Here, where one tectonic plate meets another, the seafloor is pulled down into the Earth's interior in a process called subduction. The place where this happens is marked by a deep ocean trench, the deepest features on the planet. Trenches are long, narrow depressions in the seafloor, often thousands of miles long, but only a few dozen miles wide, and they plunge to depths of more than 35,000 feet, deeper than Mount Everest is tall. The Mariana Trench, in the Western Pacific, is the deepest of them all, a place so remote and so profound that only a handful of people have ever visited it. Trenches are quiet places, almost unimaginably so. The water pressure at the bottom is more than 1,000 times greater than at the surface, enough to crush most human-made vessels like tin cans. The temperature hovers just above freezing, and the darkness is absolute. No sunlight has ever reached the floor of a trench, and no sound from the surface world penetrates to these depths. Yet even here, life exists. Strange, slow-moving creatures, adapted to the pressure and the cold, drift through the water or crawl across the sediment. Sea cucumbers, amphipods, and snailfish live their entire lives in this extreme environment, moving slowly, conserving energy, existing in a state of perpetual calm. They are a testament to the resilience of life and to the fact that even the most extreme places on Earth can be home. The process of subduction is one of the Earth's great recycling systems. As the seafloor is pulled down into the trench, it is forced beneath the adjacent tectonic plate and begins to sink into the Earth's mantle. The rock is subjected to increasing heat and pressure, and over millions of years, it melts and is reabsorbed into the Earth's interior. In this way, the seafloor that was created at the mid-ocean ridge eventually returns to the mantle, completing a cycle that takes about 200 million years. It's a slow, patient process, a reminder that the Earth is not static, but always in motion, always transforming, always cycling its materials from surface to interior and back again. Above the subduction zone, on the overriding plate, the Earth's crust is compressed and buckled, forming chains of volcanic islands or coastal mountain ranges. The pressure and heat from the subducting plate cause rock to melt, and this molten rock rises to the surface, erupting in volcanoes. The islands of Japan, the Philippines, and the Aleutians are all the result of subduction, as are the volcanic peaks of the Andes. These are dynamic, active places, but even they're governed by the same slow, deep processes that shape the rest of the seafloor. The earthquakes and eruptions that occur here are just the surface expression of forces that have been building for thousands or millions of years. And in the grand scheme of geological time, even these dramatic events are just brief punctuations in a long, slow story. Between the mid-ocean ridges and the trenches, the seafloor is constantly moving, carried along by the slow convection currents in the Earth's mantle. This movement is called plate tectonics, and it's the fundamental process that shapes our planet. The seafloor is not permanent. It is always being created at the ridges and destroyed at the trenches, always in motion, always changing. But the pace is so slow, so steady, that it's invisible to us. We live our entire lives on a planet that is constantly rearranging itself, and we never feel it, never see it, never notice. There's something deeply reassuring about that. The idea that the Earth is taking care of itself, that it has its own rhythms and cycles, and that we are simply passengers on a journey that has been going on for billions of years and will continue for billions more. The seafloor is also covered, in many places, with layers of sediment that tell the story of the Earth's history. These sediments come from many sources: dust blown off the continents, volcanic ash from eruptions, the remains of tiny marine organisms, even meteorites that have fallen from space. Each layer represents a slice of time, a record of what was happening on the Earth and in the oceans when that layer was deposited. By drilling into the seafloor and extracting cores of sediment, scientists can read this record, learning about ancient climates, ocean currents, and even mass extinctions. It's like reading a book written in mud and stone, a book that goes back millions of years, and every page is a reminder of how much has changed and how much has stayed the same. One of the most common types of sediment on the deep ocean floor is called calcareous ooze. It's made from the shells of tiny, single-celled organisms called foraminifera and coccolithophores, which live in the sunlit surface waters of the ocean. When these organisms die, their shells sink to the seafloor, accumulating in thick layers over millions of years. The ooze is soft and fine, almost like chalk, and it covers vast areas of the ocean floor, particularly in the Atlantic and Indian Oceans. It's a gentle, quiet sediment, the product of countless tiny lives, each one contributing a microscopic shell to the slow building of the seafloor. There's something peaceful about imagining this process, the way the ocean floor is built not by dramatic events, but by the patient accumulation of small things over unimaginable spans of time. In the deepest parts of the ocean, below about 15,000 feet, calcareous ooze disappears. The water at these depths is so cold and under so much pressure that it becomes slightly acidic, and the calcium carbonate shells dissolve before they can reach the bottom. Instead, the sediment here is made of siliceous ooze, composed of the shells of diatoms and radiolarians, which are made of silica rather than calcium carbonate. Silica is more resistant to dissolution, so it survives the journey to the deep seafloor. The result is a different kind of sediment, still soft, still fine, but with a slightly different texture and composition. It's a reminder that even the simplest things, like the chemistry of seawater, can shape the world in profound ways. In some places, the seafloor is covered with red clay, a sediment so fine and so slow to accumulate that it represents the most ancient and stable parts of the ocean floor. Red clay is made of dust from the continents, volcanic ash, and tiny particles of meteoric material, and it accumulates at a rate of just 1 millimeter every 1,000 years. That's even slower than the oozes, and it means that the red clay on the seafloor can be tens of millions of years old, a record of unimaginable stretches of time. The clay is called red because it contains iron oxides, rust, which gives it a deep, brick red color. It's a quiet, patient sediment, covering the most remote parts of the ocean floor, far from the continents, far from the ridges, far from any source of rapid change. Scattered across the abyssal plains, you can sometimes find nodules, small, potato-shaped lumps of metal that rest on the surface of the sediment. These are called manganese nodules, and they form through a slow process of chemical precipitation as metals dissolved in seawater gradually accumulate around a small nucleus, like a grain of sand or a shark's tooth. The nodules grow at a rate of just a few millimeters every million years, making them some of the slowest growing objects on Earth. They are rich in manganese, iron, nickel, copper, and cobalt, and they have attracted interest from mining companies. But they are also a reminder of the ocean's patience, of the way it can take the simplest chemical reactions and, given enough time, turn them into something solid and real. The seafloor is not entirely dark, even at the greatest depths. In some places, there's a faint glow, a soft blue-green light that seems to come from nowhere. This is bioluminescence, the light produced by living organisms, and it's surprisingly common in the deep ocean. Many fish, jellyfish, and other creatures produce light through chemical reactions in their bodies, using it to attract prey, communicate with each other, or confuse predators. The light is gentle, never bright, just a faint shimmer in the darkness, and it gives the deep ocean a kind of quiet magic, a sense that even in the most extreme places, there is beauty and wonder. Some of the most striking bioluminescent displays occur near hydrothermal vents, where certain bacteria glow softly in the warm water. The light is so faint that it's almost imperceptible, but it's there, a tiny beacon in the darkness, a sign of life persisting in conditions that seem impossible. It's a reminder that the deep ocean is not a dead place, not a barren wasteland, but a living, breathing ecosystem full of strange and wonderful adaptations, full of creatures that have learned to thrive in the cold and the dark and the pressure. The seafloor is also home to vast fields of cold seeps, places where methane and other hydrocarbons seep up from beneath the seafloor. Unlike hydrothermal vents, which are hot and dramatic, cold seeps are slow and quiet, releasing their gases over long periods of time. The methane provides energy for bacteria, which in turn support communities of clams, mussels, and tube worms. These cold seep ecosystems are similar to those at hydrothermal vents, but they are powered by chemistry rather than heat, by the slow breakdown of organic matter buried deep in the sediment. They are another example of the ocean's ability to create life in unexpected places, to find energy and sustenance even in the most unlikely circumstances. In some places, the methane from cold seeps freezes into a strange substance called methane hydrate, or methane ice. This is a solid, ice-like material that forms when methane and water combine under high pressure and low temperature. Methane hydrate looks like ordinary ice, but it's not made of water alone. It's a cage of water molecules trapping methane gas inside. If you were to bring a piece of methane hydrate to the surface, it would begin to melt and release the methane, which would bubble out and could even be set on fire, creating the eerie spectacle of burning ice. Vast deposits of methane hydrate exist on the seafloor, particularly along continental margins, and they represent a huge reservoir of carbon, locked away in the cold and the pressure of the deep ocean. The presence of methane hydrate has important implications for the Earth's climate. If the ocean were to warm significantly, the hydrate could melt, releasing methane into the water and eventually into the atmosphere. Methane is a powerful greenhouse gas, much more effective at trapping heat than carbon dioxide, so the release of large amounts of methane could amplify global warming. But for now, the hydrate remains stable, locked in place by the cold and the pressure, a quiet reminder of the delicate balance that governs our planet's climate. It's both a source of potential concern and a testament to the ocean's ability to store and sequester carbon, to act as a buffer against rapid change. The seafloor is also shaped by currents, though these are not the surface currents driven by wind and sun. Deep ocean currents are driven by differences in temperature and salinity, and they move slowly, almost imperceptibly, carrying cold, dense water from the poles toward the equator and warm water back toward the poles. These currents are part of a global circulation system called the thermohaline circulation, or the ocean conveyor belt, and they play a crucial role in regulating the Earth's climate. The currents move so slowly that it can take 1,000 years for water to complete a single loop around the globe, but they are powerful, carrying vast amounts of heat and nutrients, shaping the distribution of life in the ocean. As these deep currents move across the seafloor, they can erode sediment, carve channels, and even shape the underlying rock. In some places, the currents create features called sediment drifts, large mounds of sediment that accumulate on the lee side of underwater obstacles, like seamounts or ridges. These drifts can be hundreds of feet thick and stretch for miles, and they are evidence of the power of even the slowest currents, given enough time. The seafloor is not static, not unchanging. It is constantly being sculpted by the movement of water, by the slow, patient work of currents that have been flowing for thousands or millions of years. In the coldest parts of the ocean, near the poles, the seafloor can be scoured by icebergs. When icebergs break off from glaciers and drift out to sea, their deep keels can drag across the seafloor, plowing furrows and gouging trenches in the sediment. These iceberg scours are common in the Arctic and Antarctic, and they can be seen in sonar images of the seafloor, long, parallel lines stretching for miles. The scours are a reminder that even ice, floating on the surface, can shape the world beneath, and that the ocean is a place of constant interaction between surface and depth, between ice and water and stone. The seafloor is also a graveyard, a final resting place for things that have fallen from above. Whale falls are one of the most remarkable examples. When a whale dies and sinks to the seafloor, its massive body becomes a source of food and energy for deep-sea creatures. Scavengers, like hagfish and sharks, arrive first, stripping away the soft tissue. Then, for years or even decades, the bones are colonized by bacteria, worms, and other organisms that feed on the oils and nutrients locked in the whale's skeleton. A single whale fall can support a complex ecosystem for 50 years or more, providing a rare bounty of food in an otherwise nutrient-poor environment. It's a poignant reminder that even in death, there is life, that nothing is wasted in the ocean, and that every ending is also a beginning. Shipwrecks, too, become part of the seafloor, slowly being claimed by the ocean. Wooden ships are eaten by shipworms and bacteria, their timbers collapsing into piles of debris. Metal ships rust and corrode, their hulls gradually dissolving into the water. But even as they decay, shipwrecks provide habitat for marine life, becoming artificial reefs where fish shelter and corals grow. The ocean is patient with these human artifacts, slowly transforming them, reclaiming them, making them part of the natural world once more. There's something humbling about that, the way the ocean absorbs our mistakes and our losses and turns them into something new. The study of the seafloor is still in its infancy. We have better maps of the surface of Mars than we do of the ocean floor, and vast areas of the deep sea remain unexplored, unseen by human eyes. But every expedition, every sonar survey, every deep-sea dive reveals new wonders, new features, new insights into the workings of our planet. The seafloor is a frontier, a place of mystery and discovery, and yet it's also a place of profound calm, a reminder that there are still places on Earth that are wild and untouched, still places where the pace of change is measured in millennia rather than minutes. And so, as you lie here, breathing slowly, letting your body relax, you can imagine yourself drifting down through the water, past the sunlight, past the twilight, into the deep, quiet darkness of the ocean floor. You can picture the vast plains stretching out in every direction, the seamounts rising like silent sentinels, the ridges where new rock is born, the trenches where old rock returns to the earth. You can feel the weight of the water above you, not as a burden, but as a blanket, a gentle pressure that holds everything in place, that muffles all sound, that creates a space of perfect stillness. This is a world that moves slowly, that changes gradually, that exists in a timescale far beyond our own. And there is something deeply restful about that, something that invites us to slow down, to breathe, to simply be. The ocean floor holds patterns we are only beginning to understand. And among the most quietly beautiful are the fracture zones that stretch for thousands of kilometers across the deep. These are not active breaks in the earth, not places of violent movement, but rather the scars left behind by ancient offsets in the mid-ocean ridges. Where the ridge once zigzagged, where transform faults once slipped sideways as new crust was born, these fracture zones remain as long linear valleys and ridges, frozen in time. They run perpendicular to the spreading ridges, marking where different segments of the ridge were offset from one another. The rock on either side of a fracture zone can differ in age by millions of years, a testament to the patient, uneven pace of seafloor spreading. These features create subtle variations in the depth of the ocean floor, gentle undulations that influence deep currents and the distribution of sediment. They are reminders that even the most stable-looking parts of the ocean floor carry the memory of movement, written in stone and preserved in silence. Pillow lavas rest on the ocean floor in formations that seem almost organic, like frozen bubbles or stacked cushions of dark glass. They form when basaltic lava erupts underwater and meets the cold embrace of seawater. The outer surface of the lava cools instantly, forming a solid skin, while the interior remains molten and continues to push forward. This creates rounded, pillow-shaped lobes that pile upon one another, sometimes in chaotic heaps, sometimes in orderly rows. Each pillow records a single pulse of lava, a moment of creation preserved in stone. The surface of these pillows is often smooth and glassy, a type of rock called volcanic glass or basaltic glass, which forms only when cooling happens very quickly. Over time, seawater begins to alter the glass, turning it into clay minerals, but the shapes remain. Pillow lavas are found along mid-ocean ridges, on seamounts, and wherever volcanic activity meets the sea. They are quiet monuments to the meeting of fire and water, shaped by forces that are both violent and gentle, and they rest undisturbed for millions of years, blanketed slowly by sediment and time. Abyssal hills cover more of the Earth's surface than any other landform. yet few people have ever seen them or even heard their name. They are small ridges and valleys, typically only a few hundred meters high, that rise and fall across the abyssal plains. They form near mid-ocean ridges as the new crust cools and contracts, creating a corrugated texture on the seafloor. As the crust moves away from the ridge, these hills are gradually buried by sediment, smoothed over by the slow rain of particles from above. In the youngest parts of the ocean floor, near the ridges, abyssal hills stand out clearly. In older regions, they are hidden beneath thick blankets of sediment, their shapes soften but still present beneath the surface. These hills are not dramatic or steep. They are gentle, repetitive, almost monotonous in their regularity. Yet they represent the most common topography on our planet, a landscape shaped by cooling, cracking, and the patient accumulation of dust. They remind us that the Earth's surface is not defined by mountains and valleys alone, but by subtle textures that stretch across vast, unseen distances. Carbonate platforms rise from the deep in tropical and subtropical seas, built not by volcanic fire, but by the patient work of living organisms. Corals, algae, shellfish, and countless other creatures extract calcium carbonate from seawater and use it to build their skeletons and shells. When they die, their remains accumulate, layer upon layer, forming thick deposits of limestone. Over millions of years, these deposits can grow into massive platforms, some of them thousands of meters thick. The Bahamas, for example, sit atop a carbonate platform that has been growing for more than 100 million years. These platforms are sensitive to changes in sea level, climate, and ocean chemistry. When sea level rises, the platform can grow upward, keeping pace with the water. When sea level falls, the platform is exposed, and erosion begins to carve it into new shapes. Carbonate platforms are records of ancient oceans, preserving information about temperature, salinity, and the chemistry of seawater over deep time. They are places where biology and geology merge, where life itself becomes rock, and where the slow rhythms of growth and dissolution shape the seafloor. Methane seeps to certain areas of the ocean floor, releasing bubbles of natural gas from beneath the sediment. These seeps occur where methane, produced by the breakdown of organic matter deep underground, finds a pathway to the surface. The methane rises through cracks and porous sediments, sometimes forming streams of bubbles that drift upward through the water column. In cold, high-pressure environments, methane can combine with water to form methane hydrate, a solid crystalline substance that looks like ice but burns if ignited. Methane seeps create unique ecosystems. Microbes that consume methane thrive in the sediments around the seeps, and these microbes support communities of tube worms, clams, and mussels that have no need for sunlight. The methane seeps are quiet, steady sources of energy in the deep, and they have been active for thousands or even millions of years in some locations. They remind us that the ocean floor is not inert, but alive with chemical processes and slow exchanges between the earth and the sea. Salt domes rise beneath the seafloor in certain regions, created by the movement of ancient salt deposits. Millions of years ago, in shallow seas that later dried up, thick layers of salt were left behind. Over time, these salt layers were buried by sediment. Salt is less dense than the rock around it, and under pressure, it behaves almost like a very slow fluid. It begins to rise, pushing upward through the overlying sediments, forming tall columns or domes. These salt domes can be several kilometers high and several kilometers wide. As they rise, they deform the layers of sediment above them, creating folds, faults, and traps where oil and natural gas can accumulate. Salt domes are important in the petroleum industry, but they are also fascinating geological structures in their own right. They move at speeds measured in millimeters per year, yet over millions of years, they reshape the seafloor from below. They are hidden giants, silent and slow, sculpting the subsurface in ways we can only detect with seismic imaging and deep drilling. Submarine canyons are among the most dramatic features of the continental margin, cutting deep into the continental shelf and slope like river valleys carved into rock. But these canyons were not formed by rivers, at least not in the way we might think. They are shaped primarily by turbidity currents, underwater avalanches of sediment-laden water that rush down the slope at high speed. These currents are triggered by earthquakes, storms, or the buildup of unstable sediment. Once started, they carve into the seafloor, eroding rock and sediment and transporting vast amounts of material into the deep ocean. Some submarine canyons align with river mouths on land, suggesting that rivers once flowed through them during times of lower sea level. Others have no such connection and are entirely submarine in origin. The walls of these canyons can be hundreds or even thousands of meters high, and their floors are often covered with coarse sediment, gravel, and boulders carried down from the shelf. Submarine canyons are conduits, pathways that connect the shallow coastal ocean to the abyss, and they play a crucial role in transporting nutrients, carbon, and sediment into the deep sea. The Monterey Canyon, off the coast of California, is one of the largest and best-studied submarine canyons in the world. It rivals the Grand Canyon in depth and scale, plunging more than 1,800 meters below sea level at its deepest point. The canyon begins just offshore, near the town of Moss Landing, and extends more than 150 kilometers out to sea. Its walls are steep and complex, carved by countless turbidity currents over millions of years. The canyon acts as a funnel, channeling sediment, organic matter, and nutrients from the coastal zone into the deep sea. This makes it a hot spot for marine life, even at great depths. Researchers have observed deep-sea creatures, including octopuses, sea stars, and rare fish, living along the canyon walls and floor. The Monterey Canyon is also a natural laboratory, a place where scientists can study the processes that shape continental margins and the interactions between geology and biology in the deep. It is a place of quiet grandeur, hidden beneath the waves, where the earth reveals its capacity for both creation and erosion. Contorites are sedimentary deposits shaped not by gravity-driven currents flowing downslope, but by deep ocean currents flowing along the slope. These currents, driven by differences in temperature and salinity, move steadily along the continental margins, carrying fine sediment with them. Over time, the sediment settles out of the current and accumulates in thick, elongated deposits called contorite drifts. These drifts can be hundreds of meters thick and stretch for hundreds of kilometers. They are typically composed of fine-grained mud and silt, deposited slowly and evenly over millions of years. Contorites are important because they record the history of deep ocean circulation. By studying the layers within a contorite drift, scientists can reconstruct changes in current strength, direction, and sediment supply over time. They are archives of the ocean's deep movements, quiet records of circulation patterns that have shaped the climate and chemistry of the Earth for eons. The Blake Plateau, off the southeastern coast of the United States, is a broad, flat region of the seafloor that sits at a depth of about 800 meters. It is unusual because it is not covered by thick sediment, as most continental margins are. Instead, the surface of the Blake Plateau is swept clean by strong ocean currents, particularly the Gulf Stream, which flows northward along the edge of the plateau. The currents are so strong that they prevent sediment from accumulating, leaving behind a hard, rocky surface. This makes the Blake Plateau a unique environment, more like the deep ocean floor than a typical continental margin. The plateau is also notable for its deposits of methane hydrate, which lie beneath the surface in thick layers. These hydrates are stable under the cold, high-pressure conditions of the plateau, but they are sensitive to changes in temperature and pressure. The Blake Plateau is a reminder that ocean currents are powerful sculptors of the seafloor, capable of shaping the landscape in ways that are both subtle and profound. Oceanic plateaus are some of the largest volcanic features on Earth, vast elevated regions of the seafloor that rise thousands of meters above the surrounding abyssal plains. They are not part of the mid-ocean ridge system, nor are they isolated seamounts. Instead, they are massive outpourings of lava that occurred over relatively short periods of geological time, often associated with mantle plumes or other deep sources of heat. The Ontong Java Plateau in the Pacific Ocean is the largest of these features, covering an area roughly the size of Alaska. It formed about 120 million years ago in a series of enormous volcanic eruptions that released vast quantities of lava onto the seafloor. The volume of rock in the Ontong Java Plateau is comparable to that of a large continental mountain range, yet it lies hidden beneath the sea. Oceanic plateaus are important because they represent rare, catastrophic events in Earth's history, moments when the mantle released extraordinary amounts of heat and material. They may have influenced global climate, ocean chemistry, and even the evolution of life by releasing gases and altering ocean circulation. They are quiet now, submerged and still, but they carry the memory of fiery, world-changing events. Atolls are ring-shaped coral reefs that encircle a lagoon, often with no land in the center or only small, low-lying islands. They form through a slow, multi-stage process that begins with a volcanic island. First, a volcano rises from the seafloor and breaks the surface, creating an island. Corals begin to grow in the warm, shallow waters around the island, forming a fringing reef. Over time, the volcanic island begins to sink, either because the oceanic crust beneath it is cooling and contracting, or because the island is moving away from the hotspot that created it. As the island sinks, the corals continue to grow upward, keeping pace with the rising sea level. Eventually, the volcanic island disappears beneath the surface, leaving only the coral reef behind, forming a ring around a central lagoon. This process was first described by Charles Darwin during his voyage on the HMS Beagle, and it remains one of the most elegant examples of how geology and biology interact over deep time. Atolls are places of balance, where the slow sinking of the earth is matched by the patient growth of living organisms, creating structures that endure for millions of years. Foraminifera, or forams, are tiny single-celled organisms that live in the ocean and build intricate shells out of calcium carbonate. When they die, their shells sink to the seafloor and accumulate in vast numbers, forming a type of sediment called foraminiferal ooze. This ooze covers large areas of the ocean floor, particularly in regions where the water is not too deep and the calcium carbonate does not dissolve. Forams are incredibly diverse, with thousands of species, each with a distinctive shell shape. These shells are sensitive to the temperature and chemistry of the water in which they form, making them valuable tools for reconstructing past ocean conditions. By analyzing the composition and appearance of foram shells and sediment cores, scientists can determine the temperature of ancient oceans, the salinity of the water, and even the levels of carbon dioxide in the atmosphere. Forams are tiny, but they are powerful recorders of Earth's climate history, and their shells form a blanket of memory on the ocean floor, preserving information that stretches back millions of years. Radiolarians are another group of tiny marine organisms that contribute to the sediment of the deep ocean. Unlike forams, which build shells of calcium carbonate, radiolarians construct intricate skeletons out of silica, the same material that makes up glass and quartz. These skeletons are often stunningly beautiful, with delicate, lace-like patterns and symmetrical shapes. When radiolarians die, their skeletons sink and accumulate on the seafloor, forming radiolarian ooze. This type of sediment is most common in the deep ocean, below the depth where calcium carbonate dissolves, and in regions where silica-rich waters upwell from the deep. Radiolarian ooze is a fine, powdery sediment, and it covers vast areas of the Pacific Ocean floor. Like forams, radiolarians are useful for studying past ocean conditions, and their skeletons can reveal information about productivity, temperature, and circulation patterns. They are small architects of the deep, building structures of glass that endure long after their lives have ended. Diatoms are microscopic algae that live in the sunlit surface waters of the ocean and build their cell walls out of silica. They are among the most abundant photosynthetic organisms on Earth, producing a significant fraction of the world's oxygen. When diatoms die, their silica shells sink to the seafloor, where they accumulate as diatomaceous ooze. This sediment is common in cold, nutrient-rich waters, particularly in the Southern Ocean around Antarctica and in upwelling zones along the coasts. Diatomaceous ooze is light-colored, fine-grained, and rich in silica. It is also economically important. When it is buried and compressed over millions of years, it can form a rock called diatomite, which is used in filters, insulation, and other industrial applications. Diatoms are a reminder that even the smallest organisms play a crucial role in shaping the geology of the ocean floor, and that the boundary between life and rock is not always clear. The carbonate compensation depth, or CCD, is an invisible boundary in the ocean, a depth below which calcium carbonate dissolves faster than it accumulates. This depth varies depending on temperature, pressure, and the chemistry of the seawater, but it typically lies between 4,000 and 5,000 meters. Above the CCD, the seafloor is often covered with carbonate ooze, made of the shells of forams, coccolithophores, and other organisms. Below the CCD, these shells dissolve, and the sediment is dominated by clay and silica from radiolarians and diatoms. The CCD is not a fixed line. It has moved up and down over geological time in response to changes in ocean chemistry, volcanic activity, and atmospheric carbon dioxide levels. Understanding the CCD is important for interpreting the sedimentary record of the ocean floor and for predicting how the ocean will respond to future changes in carbon dioxide and acidity. It is a quiet threshold, a place where chemistry determines what is preserved and what is lost. Manganese nodules rest on the abyssal plains in certain parts of the ocean, particularly in the Pacific. These are small, potato-shaped lumps of metal-rich minerals that grow very slowly on the seafloor, accreting layers of manganese, iron, nickel, copper, and other elements over millions of years. They form around a nucleus, which might be a shark's tooth, a fragment of shell, or a piece of rock. The metals precipitate out of seawater or are concentrated by microbes living in the sediment. Manganese nodules grow at rates of only a few millimeters per million years, making them among the slowest growing geological structures on Earth. They are found in areas where sediment accumulation is very slow, so they remain on the surface rather than being buried. These nodules have attracted interest from mining companies because of their metal content, but they are also scientifically valuable as records of ocean chemistry and deep-sea processes. They are quiet, patient accumulations, formed grain by grain in the stillness of the abyss. Ferromanganese crusts coat the surfaces of seamounts and other hard substrates in the deep ocean, forming layers that can be several centimeters thick. Like manganese nodules, these crusts are rich in metals, including manganese, iron, cobalt, and rare earth elements. They grow even more slowly than nodules, at rates of only a few millimeters per million years, and they can be tens of millions of years old. The metals in the crusts are derived from seawater, and the crusts grow as metal ions precipitate onto the rock surface. Ferromanganese crusts are valuable for understanding the history of ocean chemistry, circulation, and climate. They also contain isotopes that can be used to date the crust and to trace changes in the sources of metals over time. These crusts are thin, dark coatings on ancient rock, silent witnesses to the slow chemistry of the deep sea. Polymetallic sulfides form around hydrothermal vents, where hot, metal-rich fluids are expelled from the seafloor. As the fluids mix with cold seawater, the metals precipitate out, forming chimney-like structures and deposits of sulfide minerals. These deposits contain high concentrations of copper, zinc, gold, silver, and other valuable metals. They are much younger than manganese nodules or ferromanganese crusts, forming over timescales of years to centuries rather than millions of years. Polymetallic sulfides are of great interest for deep-sea mining, but they are also important habitats for unique vent communities. The challenge is to balance the economic value of these deposits with the need to protect the fragile ecosystems that depend on them. These sulfides are records of heat and chemistry, formed at the meeting point of the Earth's interior and the ocean. Phosphorite deposits form on the seafloor in regions of upwelling, where nutrient-rich deep water rises to the surface and supports high levels of biological productivity. The nutrients, particularly phosphorus, are taken up by plankton and other organisms, and when these organisms die, their remains sink to the seafloor. Under certain conditions, the phosphorus can concentrate and form nodules, crusts, or layers of phosphorite, a rock rich in phosphate minerals. Phosphorites are economically important as a source of phosphorus for fertilizers, and they are also important for understanding the cycling of nutrients in the ocean. They form slowly, over thousands to millions of years, and they are most common on continental shelves and the upper slopes of continental margins. Phosphorites are quiet accumulations of life's essential elements, concentrated by biology and preserved in stone. Glacial dropstones are scattered across the floor of the polar oceans, solitary rocks that seem out of place in the fine mud and ooze. They were carried to the deep ocean by icebergs. During ice ages, glaciers flow into the sea and break apart, forming icebergs that drift with the currents. These icebergs often contain rocks and sediment that were picked up by the glacier as it moved over the land. As the iceberg melts, the rocks drop to the seafloor, sometimes thousands of kilometers from where they originated. Glacial dropstones are evidence of past ice ages and the extent of glaciation. They are found in sediment cores from the North Atlantic, the Southern Ocean, and other polar regions. Each dropstone is a small traveler, a piece of the land carried to the deep by ice, a reminder of the connections between the continents and the ocean floor. Bioturbation is the process by which organisms living in or on the seafloor disturb and mix the sediment. Worms, clams, crustaceans, and other creatures burrow through the mud, creating tunnels and chambers. As they move, they mix older and younger sediment layers, blur the boundaries between layers, and alter the chemical properties of the sediment. Bioturbation is most intense in shallow waters and on the continental margins, where food is abundant and animal populations are high. In the deep abyss, where food is scarce and life is sparse, bioturbation is slower and less intense, but it still occurs. The traces of bioturbation are preserved in the rock record, and they provide information about the presence and behavior of ancient organisms. Bioturbation is a form of geological activity driven by life, a slow stirring of the seafloor that connects biology and geology in intimate ways. Turbidites are layers of sediment deposited by turbidity currents, and they are among the most common types of sediment on the deep ocean floor. Each turbidite layer represents a single event, a sudden rush of sediment-laden water down the continental slope. The sediment in a turbidite is typically graded, meaning that the coarsest particles settle out first at the bottom of the layer, and the finest particles settle out last at the top. This creates a distinctive pattern that can be recognized in sediment cores and in ancient rocks that were once on the ocean floor. Turbidites are important because they transport large amounts of sediment from the continental margins to the deep sea, and they can bury and preserve organic matter, creating conditions for the formation of oil and gas. They are also hazards, capable of breaking submarine cables and damaging seafloor infrastructure. Turbidites are records of sudden events in a slow world, pulses of energy that punctuate the quiet accumulation of sediment. Hemipelagic sediment is a mixture of materials that accumulate on the continental slope and rise in the transition zone between the shelf and the deep ocean. It contains fine particles brought from the land by rivers and wind, as well as the remains of plankton that lived in the overlying water. Hemipelagic sediment accumulates more quickly than deep-sea ooze, but more slowly than the coarse sediments of the shelf. It is often rich in organic matter, which can be buried and transformed into oil and gas over geological time. Hemipelagic sediment is also a valuable archive of environmental change, recording variations in river discharge, wind patterns, ocean productivity, and climate. It is a transitional sediment, a blend of land and sea, and it covers vast areas of the ocean floor at intermediate depths. Pelagic clay, also known as red clay, is the finest and slowest accumulating sediment in the deep ocean. It is found in the most remote parts of the abyssal plains, far from land and below the carbonate compensation depth, where there is little input from biological productivity or terrestrial sources. Pelagic clay is composed of extremely fine particles, mostly clay minerals and volcanic dust, that settle out of the water column over millions of years. It accumulates at rates of only a few millimeters per thousand years, making it the slowest growing sediment on Earth. Despite its slow accumulation, pelagic clay covers about 38% of the ocean floor, a testament to the vastness and age of the deep ocean basins. It is often reddish or brown in color due to the presence of iron oxides. Pelagic clay is a sediment of patience, a blanket woven from the finest dust, settling grain by grain in the deepest silence. Sediment waves are large, regular undulations on the seafloor, similar in shape to sand dunes, but much larger and formed underwater. They are created by deep ocean currents flowing over the seafloor, which shape the sediment into long, parallel ridges and troughs. Sediment waves can be tens of meters high and several kilometers long, and they migrate slowly over time as the current moves sediment from one side of the wave to the other. They are most common in areas where strong bottom currents flow, such as in the Southern Ocean or along the continental margins. Sediment waves are visible in sonar images of the seafloor, and they provide information about the strength and direction of deep currents. They are dynamic features, constantly adjusting to the flow of water, and they remind us that even the deep ocean floor is shaped by movement and change. Channels on the deep ocean floor are carved by turbidity currents and other sediment-laden flows. These channels are similar to river channels on land, with levees on either side built up by sediment that spills out of the main flow. Some channels are hundreds of kilometers long and can be traced from the continental slope all the way to the abyssal plains. They act as conduits, funneling sediment from the margins into the deep ocean. The sediment in these channels is often coarser than the surrounding sediment, and the channels themselves are sites of active deposition and erosion. Over time, channels can shift their course, creating a complex network of old and new pathways. They are the rivers of the deep, carrying sediment instead of water, and they play a crucial role in shaping the architecture of the ocean floor. Sediment drifts are large accumulations of sediment shaped by deep ocean currents. Unlike turbidites, which are deposited by downslope flows, sediment drifts are built up by long slope currents that carry fine sediment and deposit it in elongated mounds. These drifts can be hundreds of meters thick and extend for hundreds of kilometers. They are most common along continental margins and around obstacles like seamounts, where currents are deflected and slowed down, causing sediment to settle out. Sediment drifts are important archives of ocean circulation, and they can be used to reconstruct changes in current strength and direction over millions of years. They are shaped by the invisible hand of moving water, quiet monuments to the power of slow, steady currents. Slump deposits form when sediment on the continental slope becomes unstable and slides downslope in a chaotic mass. Unlike turbidity currents, which flow as a fluid, slumps move as a coherent block, often rotating and deforming as they slide. The resulting deposit is a jumbled mixture of sediment, with folded and faulted layers. Slumps are triggered by earthquakes, rapid sediment accumulation, or changes in sea level. They are common on steep slopes and in areas where sediment accumulates quickly. Slump deposits are important for understanding the stability of continental margins and the hazards associated with submarine landslides. They are records of sudden failure, moments when the slow accumulation of sediment gives way to rapid movement. The sedimentary record of the ocean floor is a library of Earth's history, written in layers of mud, ooze, and sand. Each layer represents a moment in time, a snapshot of the conditions in the ocean and on land. By drilling into the seafloor and extracting cores, scientists can read this record, layer by layer, and reconstruct the history of climate, ocean circulation, volcanic activity, and life. The ocean floor preserves information that is often missing from the continents, where erosion and tectonic activity have destroyed much of the ancient record. The deep ocean is a place of preservation, where sediment accumulates slowly and steadily, undisturbed for millions of years. It is a quiet archive, holding the memory of the Earth and its layers. The age of the ocean floor increases with distance from the mid-ocean ridges. The youngest crust, only a few million years old, is found at the ridges, where new rock is being formed. The oldest oceanic crust, about 200 million years old, is found in the western Pacific and along the margins of the Atlantic. This is young compared to the continents, some of which are billions of years old. The reason for this difference is subduction. Oceanic crust is constantly being created at the ridges and destroyed at the trenches, recycled back into the mantle. The ocean floor is a transient feature, a surface that is constantly being renewed. This process of creation and destruction is part of the plate tectonic cycle, the great engine that drives the movement of the Earth's surface and shapes the planet over deep time. The deep ocean floor holds many quiet secrets in its layers, and among the most patient are the zones where ancient oceanic crust slowly bends and descends back into the Earth's mantle. These subduction zones mark places where one tectonic plate slides beneath another, a process so gradual that it unfolds over millions of years. The oceanic plate, dense and cool, meets the edge of a continental plate or another oceanic plate and begins its long journey downward. As it descends, it carries with it sediments, water trapped in minerals, and the memory of its time at the surface. This descent happens at rates measured in centimeters per year, a pace so slow that no human lifetime could witness significant change. Yet over geological time, entire ocean floors are recycled, returned to the heat and pressure of the mantle, melted and transformed. It is a process of renewal, quiet and thorough, happening in darkness miles below the waves. As the descending plate moves deeper, the increasing pressure and temperature cause minerals within it to release water that has been chemically bound in their crystal structures. This water rises into the wedge of mantle rock above the subducting plate, lowering the melting point of that rock and causing it to partially melt. The resulting magma is less dense than the surrounding material, so it rises slowly through the overlying plate, sometimes reaching the surface to form volcanoes. These volcanic arcs, whether they rise as island chains in the ocean or as mountain ranges on continents, are the visible expression of the subduction process. But their formation is gentle in geological terms, a slow accumulation of erupted material over hundreds of thousands of years. The magma that feeds them has traveled a long journey from deep within the Earth, carrying heat and elements from the mantle, and its arrival at the surface is the final step in a cycle that began when oceanic crust first formed at a mid-ocean ridge, perhaps thousands of kilometers away. The trenches that mark the surface expression of subduction zones are among the deepest places on Earth, and they hold a special kind of stillness. The Mariana Trench, the deepest known point in the ocean, reaches down nearly 11 kilometers below sea level. At such depths, the pressure is more than 1,000 times greater than at the surface, and the temperature hovers just above freezing. Yet even here, life persists in forms adapted to the extreme conditions. The trench floor is not a barren void, but a place where sediments settle, where microorganisms process organic matter, and where occasional visitors from the upper ocean descend as marine snow. The walls of the trench slope steeply, shaped by the bending of the oceanic plate as it begins its descent. These slopes are often marked by slumps and landslides, evidence of the instability that comes with such dramatic topography. But the overall impression is one of profound quiet, a place where the Earth's internal processes meet the ocean's depths in a slow, patient exchange. Not all subduction zones are the same, and their character depends on the age and density of the descending plate, the angle of descent, and the nature of the overriding plate. Where young, warm oceanic crust subducts, the angle of descent may be shallow, and volcanic activity in the overriding plate may be less intense. Where old, cold crust descends, the angle is often steeper, and the volcanic arc may be more vigorous. Some subduction zones produce frequent earthquakes as the plates grind past each other, while others seem quieter, their motion more continuous and less prone to sudden release. These variations create a diversity of geological settings, each with its own character and history. But in all cases, the fundamental process is the same: the slow return of oceanic crust to the mantle, the recycling of Earth's outer layer, and the creation of new rock and landscape in response. The sediments that accumulate in trenches come from many sources, and they tell stories of the ocean above and the land beyond. Rivers carry fine particles from continents, and ocean currents transport them across vast distances before they finally settle in the deep. Volcanic ash from eruptions, both on land and underwater, drifts down through the water column and adds its layers to the trench floor. The remains of marine organisms, from microscopic plankton to larger creatures, contribute organic material that feeds deep-sea communities. Over time, these sediments build up in layers, each one a record of conditions at the time it was deposited. The weight of overlying layers compresses those below, gradually turning loose sediment into solid rock. Some of these sediments are scraped off the descending plate and added to the overriding plate in a process called accretion, building up wedges of deformed rock along the trench. Others are carried down with the descending plate, eventually to be subducted and recycled. It is a sorting process, slow and mechanical, driven by the geometry of the plates and the properties of the sediments themselves. Far from the trenches, in the middle of tectonic plates, there are places where the ocean floor is remarkably flat and featureless, stretching for hundreds of kilometers with only the gentlest variations in depth. These abyssal plains, which we touched upon earlier, are the result of sediment filling in the original rough topography of the oceanic crust. But even within these plains, there are subtle structures that reveal the history of the seafloor. Buried beneath the sediment are the remains of ancient volcanic features, seamounts that were once active but are now extinct and covered. Faults and fractures in the underlying crust, though hidden, still influence the flow of water and heat through the sediment. In some places, the sediment itself has been deformed by the slow movement of the crust beneath, creating gentle folds and warps that are only visible in detailed surveys. These features are reminders that even the quietest parts of the ocean floor have a history, a story written in rock and sediment that unfolds over millions of years. Another fascinating feature of the deep ocean is the presence of manganese nodules, small potato-shaped rocks that lie scattered on the abyssal plains in certain regions. These nodules form through the slow precipitation of metals from seawater, a process that adds layers of manganese and iron oxides around a central nucleus, which might be a fragment of rock, a fossil, or even a shark's tooth. The growth rate is extraordinarily slow, often just a few millimeters per million years, making them among the slowest growing geological objects on Earth. Despite this sluggish pace, nodules can reach sizes of several centimeters across, indicating that some have been growing for tens of millions of years. They rest on the sediment surface, turned occasionally by the activity of bottom-dwelling organisms or by deep currents, which prevents them from being buried. The nodules are most abundant in areas where sedimentation rates are very low, allowing them time to grow without being covered. They represent a quiet accumulation of dissolved metals, a patient concentration of elements that would otherwise remain dispersed in the vast volume of the ocean. The distribution of manganese nodules is not random, and their presence tells us something about the conditions of the deep ocean floor. They are most common in the Pacific Ocean, particularly in a broad belt between Hawaii and Central America, where the seafloor is old, flat, and far from major sources of sediment. In regions where rivers deliver large amounts of sediment, or where biological productivity is high and organic matter rains down steadily, nodules are rare or absent, buried too quickly to grow. The chemistry of the overlying water also plays a role, as the precipitation of metals depends on the concentration of dissolved oxygen and other factors. In some areas, the nodules are accompanied by metal-rich crusts that coat exposed rock surfaces, forming through similar processes. These crusts can be even thicker than nodules, building up over millions of years on the flanks of seamounts and ridges. Together, nodules and crusts represent a slow, steady transfer of metals from seawater to solid form, a geological process that operates on timescales almost beyond human comprehension. The study of these metal deposits has revealed much about the history of the ocean and the Earth's climate. The layers within a nodule or crust can be analyzed to determine their age and the conditions under which they formed. Variations in metal content, isotopic composition, and trace elements provide clues about changes in ocean circulation, the input of metals from hydrothermal vents or continental weathering, and even the occurrence of major geological events like volcanic eruptions or asteroid impacts. In this way, these humble nodules serve as archives, recording information about the deep ocean over millions of years. They grow so slowly that they integrate long-term trends, smoothing out short-term fluctuations and preserving a record of the average state of the ocean. To hold a manganese nodule is to hold a piece of deep time, a rock that has witnessed the slow dance of continents, the rise and fall of sea levels, and the gradual evolution of life in the ocean above. In some parts of the ocean, the seafloor is marked by long, linear features called abyssal furrows or erosional grooves, carved into the sediment by deep currents. These currents, though slow by surface standards, are persistent and powerful enough to shape the soft sediment over time. The furrows align with the direction of flow, creating a grain or texture on the seafloor that can be seen in sonar images. They are evidence that the deep ocean is not stagnant, but filled with moving water, driven by differences in temperature and salinity that create density gradients. These currents are part of the global thermohaline circulation, a slow overturning of the ocean that transports heat, salt, and nutrients around the planet. The furrows are a visible trace of this circulation, a reminder that even the deepest parts of the ocean are connected to the surface and to the climate system as a whole. The interaction between currents and sediment creates a variety of bed forms on the deep ocean floor, analogous to the ripples and dunes found in rivers or deserts, but formed at much slower rates. Sediment waves, which we mentioned earlier, are one example. But there are also smaller features like ripples and lineations that reflect the local flow conditions. These bed forms migrate slowly over time as sediment is eroded from one side and deposited on the other, a process that can take centuries or millennia for even small movements. The size and shape of the bed forms depend on the strength and direction of the current, the grain size of the sediment, and the presence of biological activity that can stabilize or disturb the surface. Studying these features helps scientists understand the dynamics of deep sea currents and the transport of sediment, which in turn influences the distribution of nutrients, the burial of organic carbon, and the preservation of the geological record. In certain regions, the ocean floor is marked by fields of pockmarks, circular depressions that form when fluids escape from the sediment. These fluids can be water, methane, or other gases that have accumulated beneath the seafloor and find pathways to the surface. The release of fluid can be sudden or gradual, and it creates a pit by eroding or collapsing the overlying sediment. Pockmarks range in size from a few meters to hundreds of meters across, and they can be isolated or clustered in fields containing thousands of individual features. They are most common on continental margins where organic-rich sediments generate methane, but they can also occur in other settings where fluid flow is active. The pockmarks themselves are often sites of enhanced biological activity, as the escaping fluids bring nutrients or chemicals that support specialized communities. They are dynamic features, forming and evolving over time in response to changes in fluid pressure and sediment properties. The fluids that escape through pockmarks and other seepage sites carry dissolved chemicals from deep within the sediment, and their release can have significant effects on the chemistry of the overlying water. Methane, in particular, is a potent greenhouse gas, and its release from the seafloor has been linked to past episodes of climate change. However, much of the methane released at the seafloor is consumed by microorganisms before it reaches the atmosphere, a process that occurs in the sediment and in the water column. These microorganisms, often working in consortia with bacteria and archaea, oxidize methane and produce carbon dioxide and other byproducts. This microbial filter is an important part of the ocean's carbon cycle, preventing large amounts of methane from reaching the atmosphere and contributing to warming. The efficiency of this filter depends on factors like the rate of methane release, the availability of oxygen, and the temperature of the water, and it varies from place to place. Another intriguing feature of the deep ocean floor is the presence of brine pools, isolated pockets of extremely salty water that collect in depressions on the seafloor. These pools form when salt deposits beneath the sediment dissolve, and the resulting brine, being denser than seawater, sinks and accumulates in low-lying areas. The boundary between the brine and the overlying seawater is sharp, creating a visible interface that resembles the surface of a lake. The brine is often anoxic, lacking dissolved oxygen, and it can be toxic to most forms of life. Yet even in these extreme conditions, specialized microorganisms thrive, adapted to the high salinity and low oxygen. The brine pools are eerie and beautiful, their stillness and clarity contrasting with the surrounding seafloor. They are windows into extreme environments, places where the chemistry of the ocean is pushed to unusual limits, and they offer insights into the adaptability of life and the diversity of conditions on our planet. The salt that forms these brine pools originates from ancient evaporite deposits, layers of salt, and other minerals that were left behind when shallow seas evaporated millions of years ago. Over time, these deposits were buried by sediment and became part of the seafloor's subsurface. When seawater percolates down through the sediment and encounters the salt, it dissolves some of it and becomes a dense brine. This brine then migrates through the sediment, following pathways of least resistance, until it reaches the seafloor in pools and depressions. The process is slow and depends on the permeability of the sediment and the availability of salt, so brine pools are not common, but where they do occur, they are striking features. They have been found in the Gulf of Mexico, the Mediterranean Sea, and the Red Sea, among other places, each with its own chemical signature and biological community. The deep ocean floor is also home to vast fields of ferromanganese crusts, thick coatings of metal oxides that grow on exposed rock surfaces, particularly on seamounts and ridges. These crusts form through the precipitation of metals from seawater, similar to manganese nodules, but they grow on hard substrates rather than loose sediment. The crust can be several centimeters thick and contain high concentrations of cobalt, nickel, and rare earth elements, making them of interest for potential future mining. However, the growth rate is extremely slow, and the crusts record millions of years of ocean history. Like nodules, they can be analyzed to reveal changes in ocean chemistry, climate, and geological events. The presence of these crusts indicates that the rock surface has been exposed for a very long time, not buried by sediment, which is typical of areas with low sedimentation rates or strong currents that prevent sediment from settling. In some regions, the ocean floor is crossed by ancient scars, the traces of meteor impacts that occurred millions of years ago. These impact craters, now buried or eroded, are rare on the seafloor compared to on land or the moon, because oceanic crust is constantly being created and destroyed through plate tectonics. Most oceanic crust is less than 200 million years old, so any older craters have been subducted and lost. However, a few impact structures have been identified on the seafloor, recognized by their circular shape, disrupted stratigraphy, and the presence of shocked minerals. These craters are reminders that Earth has been bombarded by objects from space throughout its history, and that the ocean has absorbed many of these impacts. The craters themselves are often filled with sediment and difficult to detect, but advances in seafloor mapping and geophysical surveys are revealing more of these hidden scars. The ocean floor also preserves evidence of past volcanic activity that occurred not at mid-ocean ridges or hotspots, but in unusual settings related to tectonic stress or mantle upwelling. Some volcanic features are the result of small-scale melting events, localized anomalies in the mantle that produced limited amounts of magma. These features may appear as isolated seamounts or small volcanic fields, distinct from the larger structures associated with hotspots or spreading centers. Their origin can be difficult to determine, and they often require detailed study to understand the processes that created them. Each of these volcanic features is a piece of the puzzle, a clue to the complex behavior of the Earth's interior and the many ways that magma can reach the surface. In the coldest parts of the ocean, near the poles, the seafloor can be influenced by the presence of ice above. Icebergs, calving from glaciers and ice shelves, drift with currents and occasionally run aground on the seafloor in shallow areas. When they do, they scour the bottom, plowing through sediment and leaving long grooves called iceberg scours. These scours can be tens of kilometers long and several meters deep, and they are common in polar and subpolar regions. They are evidence of the power of ice, even when it is floating, and they alter the seafloor environment by disrupting sediment layers and creating depressions that can trap water or sediment. Over time, the scours are filled in by new sediment, but they remain visible in the geological record, markers of past ice activity. In some areas, the seafloor is crisscrossed with scours from multiple icebergs, creating a complex pattern that reflects the history of ice movement and ocean circulation. The deep ocean floor is also shaped by the slow process of chemical weathering, even in the absence of air and sunlight. Seawater is slightly acidic and contains dissolved oxygen and other reactive species, and over time, these chemicals react with the minerals in rocks and sediment. Basalt, the primary rock of oceanic crust, is particularly susceptible to weathering by seawater. The reactions alter the minerals, forming clays and other secondary minerals, and they release elements like calcium, magnesium, and silica into the water. This chemical exchange between rock and water is part of the global cycling of elements, and it influences the chemistry of the ocean over geological time. The weathering process is slow, but given the vast area of the ocean floor and the long timescales involved, it has a significant cumulative effect. It is one of the many quiet processes that shape our planet, operating continuously and patiently in the darkness of the deep sea. Some of the most beautiful and delicate structures on the ocean floor are the formations created by precipitating minerals in hydrothermal systems. Beyond the large chimneys we discussed earlier, there are smaller, more intricate structures like flanges, spires, and delicate crusts that form where mineral-laden water meets cold seawater. These formations can be paper-thin and fragile, built up layer by layer as minerals crystallize out of solution. They are often brightly colored, with hues of orange, red, yellow, and white, depending on the minerals present. The shapes they take are influenced by the flow of water, the rate of precipitation, and the chemistry of the fluids, and they can be remarkably complex and varied. These structures are ephemeral in geological terms, easily damaged by changes in flow or by the collapse of the larger chimney they are part of. But while they exist, they are exquisite examples of the interplay between chemistry, physics, and geology. The ocean floor is also marked by the traces of ancient life, fossils preserved in sediment that tell the story of evolution and extinction over hundreds of millions of years. While most oceanic crust is too young to contain very ancient fossils, the sediments that cover it can be much older, especially in areas far from land where sedimentation rates are low. These sediments contain the remains of plankton, shells, and other hard parts of marine organisms, and they provide a continuous record of life in the ocean. By studying these fossils, scientists can reconstruct past climates, track the movement of continents, and understand how life has responded to changes in the environment. The fossils are often microscopic, requiring careful extraction and examination, but they are abundant and diverse, offering a wealth of information. They are a reminder that the ocean floor is not just a geological archive, but a biological one as well, a place where the history of life is written in stone. In some regions, the ocean floor is covered by thick deposits of diatomaceous ooze, a sediment composed almost entirely of the silica shells of diatoms, a type of microscopic algae. Diatoms are among the most productive organisms in the ocean, and when they die, their shells sink and accumulate on the seafloor. Over time, these shells are compacted and can form a rock called diatomite, which is light, porous, and rich in silica. Diatomaceous ooze is most common in areas of high biological productivity, such as the Southern Ocean and parts of the North Pacific, where nutrient-rich waters support large populations of diatoms. The ooze is a record of this productivity, a testament to the abundance of life in the surface waters above. It is also economically important, as diatomite is used in a variety of applications, from filtration to insulation, valued for its unique physical properties. The ocean floor is also home to fields of phosphorite nodules, deposits rich in phosphorus that form in areas where nutrient-rich waters upwell and support high biological productivity. The phosphorus comes from the decay of organic matter, and it precipitates out of solution under certain chemical conditions, forming nodules and crusts on the seafloor. These deposits are found on continental margins and seamounts, often in association with ancient upwelling zones. Phosphorus is an essential nutrient for life, and phosphorite deposits are mined on land for use in fertilizers. The presence of these deposits on the seafloor indicates past periods of high productivity and favorable conditions for phosphorus accumulation. They are another example of the ocean's role in concentrating and redistributing elements, shaping the chemistry of the seafloor and the availability of nutrients for life. In the deepest parts of the ocean, where pressure is extreme and temperatures are near freezing, the seafloor is often covered by a fine, soft sediment known as red clay. This clay is composed of very fine particles, including windblown dust, volcanic ash, and the weathering products of rocks. It accumulates very slowly, at rates of just a few millimeters per thousand years, and it is found in areas far from land where other types of sediment are scarce. The red color comes from iron oxides, and the clay is often mixed with small amounts of manganese and other metals. Red clay is the most widespread type of deep-sea sediment, covering vast areas of the abyssal plains in the Central Pacific and other remote regions. It is a quiet, patient accumulation, a blanket that covers the rough topography of the oceanic crust and creates the flattest surfaces on Earth. The ocean floor is also marked by the presence of ancient lava flows, some of which are among the largest volcanic features on the planet. These flows, known as flood basalts, were erupted in massive volumes over relatively short periods of geological time, covering huge areas with thick layers of lava. On land, flood basalts are associated with major extinction events and climate changes, as the eruptions released vast amounts of gases into the atmosphere. On the seafloor, similar features exist, though they are less well known because they are hidden beneath the ocean. Oceanic plateaus, which we discussed earlier, are often the result of flood basalt eruptions, and they represent some of the largest volcanic events in Earth's history. The lava flows themselves are now cold and solid, covered by sediment, but they remain as evidence of the immense volcanic power that shaped the early ocean floor. The seafloor is also shaped by the slow process of sediment compaction, which occurs as the weight of overlying layers squeezes water out of the sediment below. This compaction reduces the volume of the sediment and increases its density, gradually transforming loose mud into solid rock. The process is slow and occurs over millions of years, but it is an important part of the rock cycle. As sediment is compacted, the pore spaces between grains decrease, and the grains are pressed closer together. In some cases, minerals precipitate from the pore water and cement the grains together, further solidifying the sediment. The result is a sedimentary rock, such as mudstone or shale, that preserves the original layering and any fossils or structures that were present. This transformation from sediment to rock is a quiet, gradual process, driven by the weight of the overlying material and the passage of time. In some areas, the ocean floor is marked by the presence of ancient river channels, now submerged and buried beneath sediment. These channels were carved when sea levels were lower, during ice ages when much of the ocean's water was locked up in glaciers. Rivers that once flowed across exposed continental shelves cut valleys into the rock and sediment, and when sea levels rose again, these valleys were flooded and became submarine features. Some of these channels are still visible on the seafloor, while others are buried and can only be detected with seismic surveys. They are evidence of the dynamic nature of sea level and the connection between the ocean and the land. The channels can also serve as conduits for sediment transport, funneling material from the shelf to the deep sea, and they influence the distribution of sediment and the shape of the seafloor. The ocean floor is also home to fields of orthogenic minerals, minerals that form directly from seawater or pore water rather than being transported from elsewhere. These minerals include carbonates, sulfides, and phosphates, and they precipitate under specific chemical conditions. Orthogenic minerals are often found in association with hydrothermal vents, cold seeps, and other sites of active fluid flow, but they can also form in more quiescent settings. The formation of these minerals is a slow process, driven by changes in temperature, pressure, pH, and the concentration of dissolved ions. They are evidence of the chemical activity of the ocean floor, the ongoing reactions between water and rock that shape the composition of the sediment and the overlying water. In some regions, the ocean floor is marked by the presence of ancient coral reefs, now submerged and often covered by sediment. These reefs formed in shallow tropical waters when sea levels were different and they were built by the slow accumulation of coral skeletons and other calcareous organisms. Over time, the reefs were drowned by rising sea levels or subsided as the seafloor sank, and they now lie at depths far below where modern corals can grow. These drowned reefs are evidence of past climates and sea levels, and they provide a record of the conditions that supported coral growth. They are also important habitats, even in their submerged state, as they provide hard substrates for attachment and shelter for a variety of organisms. The reefs are a reminder that the ocean floor is not static, but has been shaped by many changes over time, including shifts in climate, sea level, and the distribution of life. The deep ocean floor is also shaped by the process of bioturbation, which we discussed earlier, but it is worth noting again the profound effect that organisms have on the sediment. By burrowing, feeding, and moving through the sediment, organisms mix the layers, redistribute particles, and alter the chemical conditions. This biological activity can homogenize the sediment, erasing fine-scale layering and creating a more uniform texture. It can also create distinct burrows and tracks that are preserved in the rock, providing evidence of the presence and behavior of ancient organisms. Bioturbation is most intense in the upper few centimeters of sediment, where oxygen is available and food is abundant, but it can extend deeper in some settings. The effect is to create a layer of mixed sediment, a zone where the original depositional structures are modified or destroyed by biological activity. The ocean floor is also marked by the presence of sediment drifts, large accumulations of sediment that build up in areas where deep currents slow down and deposit their load. These drifts can be hundreds of meters thick and extend for tens of kilometers, and they are shaped by the interaction between currents and topography. The drifts are often elongated in the direction of flow, and they can have a streamlined shape that reflects the pattern of current movement. They are most common on continental rises and in passages between ocean basins, where currents are funneled and their speed varies. The sediment in drifts is typically fine-grained, carried in suspension by the currents, and it can contain a mix of materials from different sources. The drifts are evidence of the power of deep currents to transport and deposit sediment, and they are an important part of the sedimentary record. In some areas, the ocean floor is marked by the presence of ancient landslides, now stabilized and covered by newer sediment. These landslides, or submarine mass movements, occur when sediment on a slope becomes unstable and slides or flows downhill. The triggers can include earthquakes, rapid sedimentation, or changes in pore water pressure, and the results can be dramatic, with large volumes of sediment moving rapidly across the seafloor. Once the movement stops, the sediment comes to rest in a new location, often as a chaotic, jumbled deposit. Over time, this deposit is covered by new sediment, and it becomes part of the geological record. The landslide deposits are evidence of past instability, and they can be identified by their distinctive characteristics, such as blocks of intact sediment embedded in a matrix of finer material. They are a reminder that the ocean floor, though often stable, can experience sudden and dramatic changes. The ocean floor is also shaped by the slow process of sediment erosion, which occurs when currents are strong enough to pick up and transport particles. This erosion can create channels, grooves, and other features on the seafloor, and it can remove sediment from one area and deposit it in another. The rate of erosion depends on the strength of the current, the size and cohesion of the sediment particles, and the presence of biological or chemical factors that stabilize or destabilize the sediment. In some areas, erosion is continuous, with currents constantly reworking the seafloor, while in others, it occurs only during rare, intense events. The balance between erosion and deposition determines the shape and character of the seafloor, and it varies widely from place to place. The deep ocean floor is a place of immense scale and slow change, where processes unfold over millions of years and where the evidence of Earth's history is preserved in rock and sediment. It is a place of quiet beauty, far from the noise and bustle of the surface world, where the forces that shape our planet operate with patience and persistence. To explore the ocean floor, even in imagination, is to gain a sense of the vastness of geological time and the interconnectedness of Earth systems. It is a journey that invites us to slow down, to appreciate the gradual unfolding of natural processes, and to find peace in the knowledge that the Earth is constantly renewing itself, quietly and steadily, in the depths of the sea. The deep ocean floor holds many more quiet wonders still, and among them are the submarine landslides that occasionally reshape the seafloor. These underwater avalanches occur when sediment on a slope becomes unstable, perhaps triggered by an earthquake, or simply by the slow accumulation of material reaching a critical point. The sediment slides downward, sometimes for hundreds of kilometers, creating deposits called slide masses or slum deposits. What makes this relaxing is the knowledge that most of these events happened long ago, and the evidence they left behind is now stable, settled, and peaceful. The scars they created on the seafloor have softened over time, filled in by new sediment, and become part of the geological record. You can imagine these ancient slides as moments of movement in an otherwise still world, brief episodes now frozen in the rock, telling stories of gravity and time. And within the sediment itself, there are layers that record magnetic reversals, moments when Earth's magnetic field flipped its polarity. These reversals happen irregularly over millions of years, and each time they occur, the magnetic minerals and settling sediment align with a new field direction. When scientists study cores of ocean sediment, they can see these reversals as bands of alternating magnetic orientation, creating a striped pattern that serves as a timeline. It is a gentle reminder that even Earth's magnetic field, which seems so constant, shifts and changes over deep time. The ocean floor quietly records these shifts, layer by layer, with no fanfare, no disturbance to the surface world. It is a patient archive, holding evidence of forces we cannot see, written in the alignment of microscopic grains. In some parts of the ocean, there are features called cold seeps, similar to hydrothermal vents, but without the heat. These are places where fluids, often rich in methane or hydrogen sulfide, seep slowly from the seafloor. The fluids come from deep within the sediment, where organic material is decomposing or where ancient deposits are being squeezed by pressure. Cold seeps support unique communities of life, including tube worms, clams, and bacteria that derive energy from the chemicals in the seeping fluids. The formations around cold seeps include carbonate mounds and chimneys, built by minerals precipitating from the fluids. These structures grow slowly, over centuries, and they are often white or pale gray, standing quietly on the dark seafloor. Cold seeps remind us that life and geology are intertwined, that even in the cold and dark, there are places where chemistry and biology meet in quiet partnership. There are also underwater mud volcanoes, which are not true volcanoes but rather eruptions of mud, water, and gas from deep beneath the seafloor. These occur in areas where sediment is thick and under pressure, often near tectonic plate boundaries. The mud rises slowly through cracks and weak points, eventually reaching the surface and forming cone-shaped mounds. Some mud volcanoes are active, gently oozing material, while others are dormant, their surfaces hardened and colonized by marine life. The mud that emerges is often warm, and it can contain fragments of rock from deep layers, offering scientists a window into the subsurface. Mud volcanoes are soothing in their slowness. They do not explode or erupt violently, but rather seep and flow, reshaping the seafloor one gentle pulse at a time. In the Arctic and Antarctic oceans, there are formations called ice gouges or iceberg scours, created when icebergs drift and their keels drag across the seafloor. These scours can be meters deep and kilometers long, carving furrows into the sediment. Over time, The scours fill in with new sediment, but they remain visible in surveys of the seafloor, especially in areas that were once covered by ice sheets. Ice gouges are a record of past climates, showing where icebergs traveled and how thick the ice was. They are also a reminder of the dynamic interaction between ice and ocean, a slow dance that has shaped polar seafloors for millions of years. The scours themselves are now quiet, settled, and softened by time, holding the memory of ice in their gentle curves. There are regions of the ocean floor covered in glass. Volcanic glass formed when lava erupts underwater and cools so quickly that it does not crystallize. This glass, called hyaloclastite or volcanic glass shards, can accumulate in thick layers near underwater volcanoes. Over time, the glass weathers and breaks down, but in some places, fresh glass remains smooth and dark, a frozen moment of volcanic fire meeting cold water. The glass is fragile, and it fractures into sharp pieces, but on the deep seafloor, it lies undisturbed, a quiet testament to the rapid cooling that occurs in the deep ocean. It is soothing to think of this glass as a bridge between two extremes, heat and cold, preserved in a form that will eventually return to sediment. In some parts of the ocean, there are fields of polymetallic sulfides, deposits of metal-rich minerals formed at hydrothermal vents. These sulfides contain copper, zinc, gold, and other valuable metals, precipitated from the hot fluids as they cool. The sulfide deposits can be massive, forming chimneys and mounds that are sometimes compared to or bodies on land. Scientists and industry are interested in these deposits as potential resources, but they are also fragile ecosystems, home to unique life forms. The sulfides themselves are beautiful in their own way, with metallic luster and complex textures, and they grow slowly, adding layer upon layer over years and decades. They are a reminder that the ocean floor is not barren, but rich in minerals, chemistry, and life. There are also features called pockmarks, which we have touched on before, but it is worth noting their variety. Some pockmarks are small, just a few meters across, while others are giant, hundreds of meters wide and tens of meters deep. They form when gas or fluid escapes from the sediment, creating a depression on the seafloor. The largest pockmarks are sometimes called giant pockmarks or mega pockmarks, and they can be quite dramatic in appearance, though their formation is slow and steady. The edges of pockmarks are often colonized by organisms that thrive in the altered chemistry, and the depressions themselves become microhabitats, sheltered from currents. Pockmarks are soothing because they show that even the escape of gas can create structure and diversity, that even venting is a form of geological creativity. In the deep ocean, there are also formations called sediment waves, which we have mentioned, but they come in many forms. Some are symmetrical, like ripples, while others are asymmetrical, shaped by the direction of the current. Some sediment waves are active, moving slowly over time, while others are relict, frozen in place by changes in current patterns. The study of sediment waves helps scientists understand deep ocean currents, which are difficult to measure directly. The waves themselves are gentle, rarely more than a few meters high, and they extend for kilometers, creating a rhythmic pattern on the seafloor. They are a visual expression of invisible forces, a way for water to write its story on the sediment. There are places on the ocean floor where ancient river channels are preserved, drowned by rising sea levels thousands of years ago. These channels were carved when sea levels were lower, during ice ages, and rivers flowed across what is now the continental shelf. As the ice melted and sea levels rose, the channels were submerged, and they now lie beneath the waves, filled with sediment, but still visible in seafloor maps. These drowned channels are a connection to the past, a reminder that the boundary between land and sea is not fixed, but shifts with climate and time. They are soothing because they show that the ocean is patient, covering and preserving the landscapes that once were, holding them gently beneath the water. In some regions, there are formations called hard grounds, layers of sediment that have been cemented in a hard rock on the seafloor. This cementation happens when minerals precipitate from seawater, binding the sediment grains together. Hard grounds can form relatively quickly in geological terms, and they create a firm surface that is different from the soft sediment around them. These hard surfaces are often colonized by organisms that need a stable place to attach, such as corals, sponges, and bryozoans. Hard grounds are a reminder that the seafloor is not uniform, that within the softness there are patches of firmness, creating diversity in texture and habitat. They are soothing because they represent stability, a place where the sediment has found a more permanent form. There are also features called sediment drifts, which we have mentioned, but they deserve further reflection. These drifts can be enormous, containing vast amounts of sediment deposited over millions of years. Some drifts are located near the outlets of ocean currents, where the current slows and drops its sediment load. Others form in the lee of underwater obstacles, where the current is deflected and sediment settles. The drifts are layered, with each layer representing a period of deposition, and they can be studied to understand changes in ocean circulation over time. The drifts themselves are gentle, sloping features, and they are often smooth and undisturbed, a testament to the steady work of currents over deep time. In the ocean, there are also formations called orthogenic carbonates, which form directly on the seafloor rather than settling from above. These carbonates precipitate from seawater when conditions are right, often in areas where methane seeps or organic matter is abundant. The carbonates can form nodules, crusts, or even large mounds, and they are often associated with microbial activity. The microbes facilitate the precipitation by altering the chemistry of the surrounding water, creating conditions where carbonate minerals can form. Orthogenic carbonates are soothing because they show that the ocean floor is chemically active, that minerals are not just deposited, but also created in place through the quiet work of chemistry and life. There are regions of the ocean floor where the sediment is dominated by volcanic ash, deposited after eruptions on land or underwater. This ash settles through the water column, sometimes traveling thousands of kilometers from its source, and it accumulates on the seafloor as a distinct layer. Over time, the ash weathers and alters, but it remains recognizable, and it serves as a marker layer that can be traced across wide areas. Volcanic ash layers are useful for dating sediment cores because they can often be linked to known eruptions. They are soothing because they show that even events on land leave their mark on the deep ocean, that the Earth is connected, and that the ocean quietly receives and records what the atmosphere delivers. In some parts of the ocean, there are features called brine lakes, which we have touched on, but they are worth revisiting. These lakes are depressions on the seafloor filled with water that is much salter and denser than the surrounding seawater. The brine does not mix easily, so it forms a distinct layer with a visible boundary that looks almost like a shoreline. Some brine lakes are anoxic, lacking oxygen, and they are hostile to most life, though some specialized bacteria thrive there. The brine itself is often rich in dissolved minerals, and it can preserve organic material that falls into it. Brine lakes are soothing because they are so strange and still, pockets of extreme chemistry sitting quietly on the seafloor, undisturbed by the water above. There are also formations called ferromanganese nodules, which we have mentioned, but they come in many varieties. Some are smooth and round, while others are lumpy and irregular. Some are small, like marbles, while others are large like grapefruits. The nodules grow in concentric layers, like tree rings, and their composition varies depending on the chemistry of the surrounding water. Scientists study nodules to understand the geochemical cycles of the ocean, and they have found that nodules can record changes in ocean chemistry over millions of years. The nodules themselves are soothing because they are so slow-growing, so patient, adding layer upon layer in the quiet darkness. In the deep ocean, there are also features called abyssal furrows, which are long, linear grooves carved in the seafloor by deep currents. These furrows can be meters deep and extend for kilometers, and they are aligned with the direction of the current. The currents that create them are slow but persistent, eroding the sediment over long periods of time. Abyssal furrows are a reminder that even the deepest ocean is not still, that there are currents moving through the abyss, shaping the seafloor in subtle ways. The furrows themselves are gentle, softened by sediment that settles into them, and they are often only visible in detailed seafloor maps. There are regions of the ocean floor where the sediment is rich in phosphorite, a mineral that forms from the accumulation of phosphorus, often derived from marine organisms or upwelling currents. Phosphorite can form nodules, crusts, or layers, and it is most common in areas where biological productivity is high. The phosphorus in phosphorite is an essential nutrient, and its accumulation on the seafloor represents a long-term storage of this element. Over geological time, some phosphorite deposits have been uplifted and mined on land for use as fertilizer. On the ocean floor, phosphorite is a quiet reminder of the connection between life and minerals, of how organisms concentrate elements and leave them behind in the sediment. In some parts of the ocean, there are features called mud waves, which are similar to sediment waves but composed of finer material. Mud waves form in areas where fine-grained sediment is transported by weak currents, and they are often found in deep basins or on the lower parts of slopes. The waves are small, usually less than a meter high, and they are spaced closely together, creating a rippled texture on the seafloor. Mud waves are soothing because they show that even the finest sediment can be organized into patterns, that even the weakest currents can leave their mark. The waves themselves are delicate, easily disturbed, but in the deep ocean, they can persist for long periods, undisturbed by storms or surface activity. There are also formations called drop stones, which are rocks that have been carried by icebergs and dropped onto the seafloor when the ice melts. These stones are often far from any source of similar rock, and they stand out against the fine sediment around them. Drop stones are most common in polar and subpolar regions, but they can also be found in areas that were once glaciated. They are a record of past ice ages, showing where icebergs traveled and how far they drifted before melting. Drop stones are soothing because they are solitary and still, resting quietly on the seafloor, holding the memory of ice and their composition and placement. In the ocean, there are also features called sediment mounds, which are accumulations of sediment that rise above the surrounding seafloor. These mounds can form in many ways: by the buildup of biogenic material, by the deposition of sediment in the lee of an obstacle, or by the growth of authigenic minerals. Some sediment mounds are small, just a few meters high, while others are large, rising tens of meters above the seafloor. The mounds are often colonized by organisms that benefit from the elevated position, such as corals and sponges. Sediment mounds are soothing because they show that even in the flatness of the abyssal plain, there is variation, that the seafloor is not monotonous, but full of subtle topography. There are regions of the ocean floor where the sediment is dominated by siliceous ooze, which we have mentioned, but it is worth noting the variety within this category. Some siliceous oozes are made mostly of diatom frustules, while others are rich in radiolarian skeletons. The composition depends on the dominant plankton in the overlying water, which in turn depends on temperature, nutrient availability, and other factors. Siliceous oozes are most common in polar regions and in areas of upwelling, where nutrients are abundant and diatoms thrive. The ooze itself is soft and fine, and it can be meters thick, representing millions of years of accumulation. It is soothing to think of this ooze as a blanket of microscopic glass, gently covering the seafloor, holding the remains of countless tiny lives. In some parts of the ocean, there are features called contorite drifts, which we have touched on, but they are worth further exploration. These drifts are shaped by deep ocean currents, which flow along the contours of the seafloor, depositing sediment in specific patterns. The drifts can be enormous, extending for hundreds of kilometers, and they are often layered, with each layer representing a period of deposition. The study of contourite drifts helps scientists understand the history of ocean circulation, because the drifts record changes in current strength and direction over time. The drifts themselves are gentle, sloping features, and they are often smooth and undisturbed, a testament to the steady work of deep currents. There are also formations called ferromanganese crusts, which we have mentioned, but they deserve further reflection. These crusts grow on hard surfaces, such as seamounts, ridges, and exposed bedrock, and they can be several centimeters thick. The crusts grow by the slow precipitation of iron and manganese from seawater, along with other metals such as cobalt, nickel, and rare earth elements. The growth rate is extremely slow, often just a few millimeters per million years, making ferromanganese crusts some of the slowest growing geological formations on Earth. The crusts are layered, with each layer recording the chemistry of the ocean at the time it formed. They are soothing because they are so patient, so slow, adding layer upon layer in the quiet darkness, undisturbed by the passage of time. In the deep ocean, there are also features called sediment fans, which are large, fan-shaped deposits of sediment at the mouths of submarine canyons. These fans form when sediment-laden currents, called turbidity currents, flow down the canyon and spread out onto the abyssal plain. The sediment settles in layers, with the coarsest material near the canyon mouth and the finest material farther out. Sediment fans can be enormous, covering thousands of square kilometers, and they are often hundreds of meters thick. The fans are a record of sediment transport from the continents to the deep ocean, and they show how rivers, even those far inland, can influence the seafloor. Sediment fans are soothing because they are so gradual, built layer by layer over millions of years, a quiet testament to the power of gravity and water. There are regions of the ocean floor where the sediment is rich in glauconite, a green mineral that forms in shallow marine environments and is sometimes found in deeper waters. Glauconite forms when potassium, iron, and other elements are incorporated into clay minerals, creating a distinctive green color. The presence of glauconite in sediment indicates slow deposition and specific chemical conditions, and is often associated with periods of low sedimentation rate. Glauconite is soothing because it is so distinctive, a splash of green in the otherwise gray or brown sediment, a marker of specific conditions and slow time. In some parts of the ocean, there are features called slump scars, which are the marks left on the seafloor by submarine landslides. These scars are depressions or irregular surfaces where sediment has been removed, and they can be quite large, extending for kilometers. Over time, the scars fill in with new sediment, but they remain visible in seafloor surveys for long periods. Slump scars are a record of past instability, showing where the seafloor was once steep or where an event triggered a landslide. They are soothing because they are now stable, the movement long past, and the scars are being gently erased by the slow accumulation of new sediment. There are also formations called biogenic reefs, which are built not by corals, but by other organisms, such as sponges, oysters, or worms. These reefs form in a variety of environments, from shallow shelves to deep slopes, and they create complex structures that provide habitat for many other species. The organisms that build these reefs secrete hard materials or bind sediment together, creating a framework that grows over time. Biogenic reefs are soothing because they show that life can create structure, that organisms working together can build something lasting and complex, even in the challenging environment of the ocean floor. In the ocean, there are also features called sediment waves, which we have mentioned several times, but they are worth one more reflection. These waves are not just passive features. They're dynamic, moving slowly over time as currents shift and sediment is redistributed. Some sediment waves migrate upslope, while others move downslope, depending on the current direction and the sediment supply. The movement is slow, often just centimeters per year, but over thousands of years, the waves can migrate significant distances. Sediment waves are soothing because they show that the seafloor is not static, but slowly, gently in motion, shaped by forces that are patient and persistent. There are regions of the ocean floor where the sediment is rich in barite, a heavy mineral that forms from the precipitation of barium sulfate. Barite is often associated with hydrothermal vents or areas of high biological productivity, where barium is concentrated in the water. The mineral forms small crystals or nodules, and it can accumulate in layers on the seafloor. Barite is soothing because it is dense and stable, a heavy mineral that settles quickly and remains in place, adding weight and substance to the sediment. In some parts of the ocean, there are features called erosional remnants, which are isolated patches of older sediment or rock that have been left behind by erosion. These remnants stand above the surrounding seafloor, protected by their hardness or composition, while softer material around them has been eroded away. Erosional remnants are a record of past conditions, showing what the seafloor once looked like before erosion reshaped it. They are soothing because they are survivors, standing quietly in the present, holding memories of the past, shaped by forces that have long since moved on. There are also formations called sediment ponds, which are small, flat-bottom depressions on the seafloor that have filled with sediment. These ponds form in areas of rough topography, such as between seamounts or in the crests of mid-ocean ridges, where sediment settles into low spots. The ponds are often smooth and level, contrasting with the rugged terrain around them. Sediment ponds are soothing because they are pockets of calm in a landscape of variation, places where sediment has found a resting place and settled into stillness. In the deep ocean, there are also features called hydrothermal mounds, which are accumulations of minerals and sediment around hydrothermal vents. These mounds are built by the precipitation of minerals from vent fluids, combined with sediment that settles from the water column. The mounds can be meters to tens of meters high, and they are often colonized by vent organisms. Over time, as vents become inactive, the mounds are buried by sediment, but they remain as features in the subsurface, visible in seismic surveys. Hydrothermal mounds are soothing because they show that even after the heat and activity have ceased, the structures remain quiet and solid, a record of past energy. There are regions of the ocean floor where the sediment is rich in zeolites, minerals that form from the alteration of volcanic ash and seawater. Zeolites have a porous structure, and they can absorb and exchange ions, making them chemically active. The presence of zeolites in sediment indicates that volcanic material has been altered over time, and it provides information about the chemical conditions of the ocean. Zeolites are soothing because they are transformative, showing that even ash can become something new, that the ocean is a place of slow chemical change. In some parts of the ocean, there are features called tectonic scarps, which are steep cliffs or slopes created by faulting. These scarps mark the edges of tectonic plates or blocks of crust that have moved relative to each other. The scarps can be hundreds of meters high, and they are often sharp and dramatic in appearance. Over time, sediment accumulates at the base of the scarp, softening its profile, but the scarp remains as a prominent feature. Tectonic scarps are soothing because they are evidence of past movement, now frozen in place, the energy that created them long since dissipated. There are also formations called sediment lobes, which are fan-shaped deposits at the ends of submarine channels. These lobes form when sediment-laden currents emerge from a channel and spread out onto the seafloor, depositing their load in a broad, lobate shape. The lobes are layered, with each layer representing a separate flow event. Over time, Multiple lobes can overlap, creating a complex pattern of deposition. Sediment lobes are soothing because they're the end of a journey, the place where sediment comes to rest after traveling down a canyon and through a channel, finally settling into stillness. In the ocean, there are also features called pelagic drapes, which are thin, uniform layers of sediment that cover the seafloor like a blanket. These drapes are composed of fine-grained material that settles slowly from the water column, and they are most common in areas far from land, where there is little input from rivers or turbidity currents. Pelagic drapes are soothing because they are so even, so gentle, covering the seafloor with a smooth, continuous layer that speaks of slow, steady accumulation over vast stretches of time. There are regions of the ocean floor where the sediment is rich in clay minerals, which form from the weathering of rocks on land and are transported to the ocean by rivers and wind. Clay minerals are extremely fine-grained, and they settle very slowly through the water column, taking years or even decades to reach the deep seafloor. Once there, they accumulate in thick layers, creating a soft, cohesive sediment. Clay minerals are soothing because they are so fine, so gentle, a record of the slow breakdown of continents and the patient transport of material to the sea. And as we draw toward the close of this gentle journey, it is worth reflecting on the overall character of the ocean floor. It is a place of immense scale, covering more than 70% of Earth's surface, yet it remains largely unseen and unexplored. The formations we have discussed, the ridges and trenches, the plains and seamounts, the vents and seeps, the sediment and minerals, all exist in a realm of darkness, cold, and pressure, far removed from the world we inhabit. Yet they're not separate from us. The ocean floor is connected to the continents by the movement of tectonic plates, to the atmosphere by the exchange of gases, to life by the cycling of nutrients. It is a quiet foundation, a patient archive, a place where time moves slowly and change is measured in millions of years. The ocean floor is also a place of beauty, though few will ever see it directly. The formations we have explored are sculpted by forces that are both powerful and gentle, by the slow creep of tectonic plates, the steady fall of sediment, the patient work of currents, the quiet chemistry of minerals. These forces create shapes and patterns that are elegant in their simplicity, rhythmic in their repetition, and profound in their scale. The ocean floor is a landscape of subtlety, where the drama is muted, where the action is slow, and where the result is a quiet grandeur. And perhaps most soothing of all is the knowledge that the ocean floor will continue its slow work long after we are gone. The plates will keep moving, the sediment will keep settling, the minerals will keep precipitating, the currents will keep flowing. The ocean floor is a testament to the patience of the earth, to the power of slow processes, to the beauty of deep time. It is a place where we can rest our minds, knowing that some things are beyond the rush of daily life, beyond the noise and urgency of the surface world. The ocean floor is a place of peace, a place of stillness, a place where time itself seems to slow down. As you lie here, breathing softly, you can imagine yourself drifting down through the water column, past the sunlit surface, through the twilight zone, into the darkness of the deep. You can imagine the slow descent, the gradual increase in pressure, the cooling of the water, the fading of light. And then, gently, you reach the seafloor, and you see it spread out before you, vast and quiet, covered in soft sediment, dotted with seamounts and ridges, marked by the slow work of geological time. You can imagine resting there, on the abyssal plain, surrounded by stillness, cradled by the weight of the ocean above, held in the embrace of deep time. There is no need to move, no need to speak, no need to do anything at all. The ocean floor asks nothing of you. It simply exists, patient and calm, a place where the earth is at work in the slowest, gentlest ways. You can let your thoughts drift like sediment, settling slowly, finding their place, coming to rest. You can let your body relax, heavy and still, like a rock on the seafloor, undisturbed by currents, held in place by gravity and time. And if you find yourself still awake, still listening, know that there are more stories to tell, more formations to explore, more wonders waiting in the deep. But there is no hurry. The ocean floor has been here for millions of years, and it will be here for millions more. It is patient, and it invites you to be patient too, to rest, to breathe, to let go of the urgency of the surface world and sink into the stillness of the deep. So let yourself rest now, knowing that you are held, that you are safe, that the earth beneath you is solid and patient and calm. Let the knowledge of the ocean floor, of its slow processes and quiet beauty, wash over you like a gentle current, carrying away tension, carrying away worry, leaving only peace. The ocean floor is a place of rest, and you are welcome there in your imagination, in your mind, in the quiet space where sleep begins. And so, as we come to the end of this journey, I wish you a gentle night, a peaceful rest, a deep and restorative sleep. May your dreams be as calm as the abyssal plains, as steady as the sediment settling, as patient as the minerals precipitating in the dark. May you wake refreshed, carrying with you the quiet knowledge of the ocean floor, a reminder that there is beauty in slowness, peace in patience, and wonder in the deep. Good night, and rest well.